so this is our AP Chemistry Chapter 17 lesson video. This is part 4, and in this video I'm going to cover section 17.6. So if you have just been struggling to get through all these videos about equilibrium, we are finally at the last one. So let's knock this out, and then we can move on to bigger and better things. Alright, so in 17.6 we're going to talk about precipitation and separation of ions. And so we're going to talk about how you know whether a precipitate's going to form or not, and we'll do something called selective precipitation, where you have multiple options of a precipitate, and so you'll determine which one would be most likely to form. So just like when we first learned equilibrium, or your K must have equilibrium concentrations. However, if you want to use initial, then what you're technically solving for is Q. And so for Q, you can use initial amounts instead of equilibrium. And then based on how Q and K relate, you can determine whether or not a precipitate will form. So if Q is greater than K, so first of all, let's not forget that Q and K are just products over reactants. But when we're talking about precipitation, because our reactants is solids, really it's just products. Alright, so if Q is too large, that means I have too many products. So precipitation will occur because it's going to shift to the reactants, which is a solid. Making a solid is a precipitate. That will happen, and it will precipitate until your Q equals your KSP. On the other hand, if Q is equal to KSP already, equilibrium is already happening, and we have a saturated solution. If Q is less than KSP, that means we don't have enough products. So we need to make more products, and so that means the solid is going to dissolve until Q equals KSP. So the important thing to remember is we have a solid making two aqueous. Remember, that's basically what we have happening. Okay, so if we have too many products, it will shift to make the solid, which is precipitation. If we don't have enough products, it will shift to make more products, which are both aqueous. So in that case, you would not have precipitation. Alright, so let's look at some of these together. So the first one, it says, will a precipitate form when 0.1 liters of 8.0 times 10 to the negative 3 molar lead-2 nitrate is added to 0.4 liters of 5 times 10 to the negative 3 molar sodium sulfate? And then it tells me the KSP is 6.3 times 10 to the negative 7. Alright, so what I need to do first is I need to figure out how many moles of these things am I dealing with. Okay, so I got 0.1 liters of this much molarity lead-2 nitrate, and I got 0.4 liters of this molarity sodium sulfate. Alright, so the first thing I'm going to do is, and so what I'm looking at is the precipitate that could possibly form. Remember, sodium and nitrate are spectators, is lead sulfate, lead-2 sulfate. That's my possible precipitate. That's what I'm looking at. Is that going to form? Alright, so I start with my lead only, so I have 8 times 10 to the negative 3 molar times 0.1 liter, and that gives me 8 times 10 to the negative 4 moles of PB. Because of course, one of these gives me 1 mole of PB. It's a 1-to-1 ratio. However, I do have to consider the fact that I have a dilution that has occurred, because once we mix these two together, it's no longer just the 0.1 liter. Now it's 0.5 liters because I have to combine them. So in other words, right here, I'm just doing a dilution. That's all that's happening. So I divide by that 0.5 because that's my total volume. And so I get that currently I have a new concentration, now that it's been diluted, of 1.6 times 10 to the negative 3 molar lead nitrate. Lead, because we're not interested in the nitrate. Alright, so then I look at my sulfate. So I have 5.0 times 10 to the negative 3 molar times 0.4 liters, and that's going to give me 2 times 10 to the negative 3 moles of the sulfate. And remember, it is a 1-to-1, okay? One of these makes 1 sulfate. You do have to keep that in mind. Like if I was doing sodium, then one of these actually makes 2 sodium ions, but I'm not interested in sodium. I also have to do that same dilution with my total volume. And so you could use M1B1 equals M2B2 if you wanted to for this instead. And so I get 4 times 10 to the negative 3 molarity for my sulfate. Okay, now these are what I'm starting with. This isn't equilibrium, so I'm going to plug this into Q. So without writing the reaction, I'm going to say, okay, this is clear. Well, I'll just go ahead and write the reaction. So this is clearly going to break up into PB and SO4. All right, so my Q is my PB, so I'll plug that in. So 1.6 times 10 to the negative 3. I'm going to leave off units because Q and K don't have any units, times my sulfate, which is 4 times 10 to the negative 3. And so once I multiply those, I got 6.4 times 10 to the negative 6. Well, if you look, KSP is 6.3 times 10to the negative 7. So this is 10 to the negative 7, this is 10 to the negative 6. That means Q is greater than KSP. That means I have too many products. So if I have too many products, it's going to shift to the reactants, and I am going to form a precipitate. So yes, a precipitate will form because Q is greater than KSP. So it's going to shift to the solid and make a precipitate. All right, so let's see if you can try one of these on your own. All right, so y'all try this one. I'll assume you paused it, tried it, and we'll look at it together. So it says, will a precipitate form when 0.05 liters of 2 times 10 to the negative 2 molar NaF is mixed with 0.01 liters, that should say of 1 times 10 to the negative 2 molar CaNO3. Okay, well again, we know sodium and nitrate are spectators, so what we're looking at is calcium and fluorine bonding. So the thing you have to keep in mind though are balancing those charges. Okay, so it's going to be CaF2 breaking up into Ca and 2F minus. Okay, so see this one's going to have a little bit different because it's not all 1 to 1 here. Okay, so we start the same way. First we need to get the new molarities now that we've mixed them together. Okay, so I start with my calcium, and I have 1 times 10 to the negative 2 molar times 0.01 liters, and that gives me 1 times 10 to the negative 4 moles of calcium. But I need to do the dilution, so once I combine these, I'm going to have 0.01 plus 0.05 liters, so I'm actually going to have 0.06 liters. And so once I do that, I get a new concentration of 1.67 times 10 to the negative 3 molar for my calcium. And I don't have to do anything because 1 of calcium nitrates makes 1 calcium. All right, so now I move on to my fluorine, or my fluoride since it's negative. So I have 2 times 10 to the negative 2 molar times 0.05 liters. And so for that, I got 1 times 10 to the negative 3 moles of fluoride ions. But I got to divide by that new total. Okay, that's the important thing, is once you combine two things, if you need to use molarities, you have to do a dilution first. All right, and so once I did that, I got 1.67 times 10 to the negative 2 molar of my fluoride ions. Okay, so let's write that KSP just to remind you how to do that. So KSP is, of course, calcium times fluoride, but I need to square it. Don't forget to square it. All right, and remember, we leave off the reactant because it's a solid. But I don't have equilibrium values. I have starting amounts, so I'm just going to call this Q instead. So Q equals my calcium. So I pull this number right here, 1.67 times 10 to the negative 3. Look, let me leave off units because K and Q have no units. Times my fluorine. But don't forget, fluorine is, or the fluoride ion is squared. Okay, so once I solve for that, I got 4.66 times 10 to the negative 7. And my KSP is, oh, whoops, I forgot to give you all the KSP. Just letting you know, the KSP is, good thing I have it written on my paper, 3.9 times 10 to the negative 11. So if you look, Q is to the negative 7, KSP is to the negative 11. That means Q, again, is greater than KSP, so yes, a precipitate will form. Just like that, okay? So if for some reason Q had been less, like say this was 10 to the negative 17, and KSP is 10 to the negative 11, then precipitation would not form, or would not happen. And if they were equal, then we would say it's already at equilibrium and you have a saturated solution. All right, so that's how you can determine if you have enough for precipitation or not. All right, so now let's talk about selective precipitation. So selective precipitation is separation of ions in an aqueous solution by using a reagent that form a precipitate with one or a few of the ions. The substance that will precipitate first is the one with the lowest concentration of ions required. So what we would do is we would calculate how much concentration for each precipitate option of ions that we would need, and the lowest amount is the one that would precipitate first. All right, so let's look at the first one together. So the first one says, a solution contains 1 times 10 to the negative 2 molar silver ions and 2 times 10 to the negative 2 molar lead ions. When chloride ions is added to the solution, both AgCl and PbCl2 could precipitate from the solution. Okay, and so it gives us the KSP for the AgCl and the KSP for the PbCl2. So it says what concentration of Cl- is necessary to begin precipitation of each salt, and which salt will precipitate first. Okay, so we got a lot of things that we got to figure out. So first we need to figure out how much chlorine to make each one precipitate, and then we can pick the lowest one as the one that would precipitate first. All right, so what I did here was I said, okay, well we got AgCl going to Ag positive and Cl negative, and so I set up my whole KSP for this. So KSP is the silver ion times the chloride ion. And so then I just plugged in. So my KSP for the AgCl is 1.8 times 10 to the negative 10. And then it told me the silver concentration is 1 times 10 to the negative 2. And then I can solve for the chloride ion concentration because I don't know that one. Okay, so once I solve, I get that it needs a chloride concentration of 1.8 times 10 to the negative 8 molar. So that's how much chloride ion I would need in order to precipitate the AgCl. So now I do the same thing for the PbCl2, but you got to be careful on that one. This is why writing the reaction will sometimes help you from making mistakes. Okay, so we have Pb with a positive 2, and we have 2 Cl negatives, because remember that changes our KSP. So KSP is of course our lead times our chloride, but we got to square it because it's of course has a 2 in front. So then I'm ready to plug in. So my KSP for the lead chloride is 1.7 times 10 to the negative 5, and then it told me the lead concentration is 2 times 10 to the negative 2, and that multiplied by my Cl squared. So you got to be careful, this is squared. So once I divide the 2 times 10 to the negative 2 to the other side, I'm going to have to square root it. Okay, so don't forget to square root it. So I solve for my Cl, and I get that it takes 2.92 times 10 to the negative 2 molar. Okay, so this is how much chloride ion it takes to precipitate PbCl2. This is how much it takes to precipitate AgCl. So then when it says which salt will precipitate first, I just pick the lower amount. So since 10 to the negative 8 is smaller than 10 to the negative 10, that means AgCl will precipitate first. Okay, so all we had to do was we had to solve for the chloride ion concentration of each one, and then the lower the concentration, the sooner it's going to precipitate. All right, so let's see if you can try one of these. And so be careful for those coefficients. Don't forget about those in the K values. All right, so you try this one. I'll assume you paused it, tried it, and we'll look at it together. All right, so it says the solution consists of 0.05 molar magnesium ions and 0.02 molar copper ions. Which ion will precipitate first as OH minus is added to the solution? What concentration of OH minus is necessary to begin precipitation of each ion? And then it gives me my 2 KSPs. Okay, so it's the same question. How much OH do we need to precipitate both of them? And then which one is going to precipitate first? And of course, that's the one that has the lowest concentration of OH minus necessary. Okay, so I'm going to write my reactions first, just because every now and then you are likely to mess up if you don't actually write it out. So we have our Mg positive 2 and 2 OH minus. That's to remind you, you've got to square that one. So of course my KSP is the magnesium ion times the hydroxide ion squared, because I have that 2 right there. So then I just plug in. So my KSP is 1.8 times 10 to the negative 11, and that equals, it told me my magnesium concentration is 0.05. Whoops, sorry, it says 0.05 and I just wrote 0.5. Times my OH concentration squared. Okay, so don't forget about that squared. You're going to have to square root it when you're solving. So for the magnesium hydroxide to precipitate, I got that we needed 1.9 times 10 to the negative 5 molar OH minus. But we don't know if that's going to precipitate first or not until we check the CuOH. So we have CuOH2. So again, it's going to break into Cu with a positive 2 and 2 OH minus. All right, so my KSP is the Cu positive 2 and the OH minus squared. Don't forget about that squared. And then I plug in. So my KSP for the copper compound is 4.8 times 10 to the negative 20. And so then I plug in my copper amount, which was 0.02 times OH minus squared. So don't forget, you're going to need to square root it. So once I solve for OH minus, I ended up getting 1.55 times 10 to the negative 9 molar. Okay, so I answered this part, what concentration of OH is necessary to begin each precipitation. So there's my two answers, but then we still have to answer what's going to precipitate first. So 10 to the negative 5 is larger than 10 to the negative 9. So that means this needs less OH before it'll start precipitating. So CuOH2 is going to precipitate first, just like that. Okay, so hopefully that's not really that bad. We didn't even have to do an ice chart or anything for this. Or a bar chart. The bar charts are the worst ones. All right, our last one, sample integrative exercise. Okay, so it says a sample of 1.25 liters of HCl gas at 21 degrees Celsius and 0.95 atm. So y'all, once I start seeing a volume, a temperature, a pressure, I can start thinking PV equals nRT. Is bubbled through 0.5 liters of 0.15 molar NH3. Okay, so in other words, I have strong acid and I have a weak base. Oh man, we all know where this is headed. Calculate the pH of the resulting solution, assuming that all the HCl dissolves and that the volume of the solution remains at 0.5 liters. So in other words, we have an odd way of doing a titration here, where one of them just happens to be a gas instead of a liquid. So this is fantastic, of course, because now we got strong and weak, so you know those are the longest. So let's just go ahead and power through. In this case, they gave me odd information for my strong acid, but remember, when we're doing a titration or a neutralization of any type, we need to get to moles. So since I know my volume and my pressure and my temperature, I can use PV equals nRT. Okay, so I'm going to use PV equals nRT, but I'm going to solve for N. So it's PV over RT. So I plug in my pressure of 0.95 atm. I plug in my volume of 1.25 liters. I plug in my R of 0.0821 liters times atmospheres over moles times Kelvin. And I plug in my temperature. So 21, of course, we add 273, and we end up getting 294 Kelvin. Don't forget about changing Celsius to Kelvin. Just because we haven't done gas laws in a while doesn't mean we don't still do the same thing. So once I solved for that, I got that we had 0.049 moles of my H+. Because of course this is strong acid, so it's fully going to break up. So now I got to figure out what's going on with my base. So I know how much, and I know the molarity, so I can solve for moles for base 2. So for moles of my base, let's see, I'll do that kind of right over here because I don't have a whole lot of room and I got to do a bar chart down here. So let me try to save as much room as I can. So I did my 0.15 molar times my 0.5 liters, and I got 0.075 moles of my base. Okay, so now I know how much acid, I know how much base. I can clearly see I have more base than acid, so that makes me expect that my pH would be greater than 7. Alright, so then I set up my bar chart. So we're going to have our NH3, it's going to react with the H+, and it's going to form that NH4 positive. Okay, so we do our before addition, addition, after addition. So before addition, I have this many moles of my NH3, so 0.075. It didn't tell me I have any H plus to start with, and it didn't tell me I have any of my conjugate acid to start with, so I put 0 for this. My addition of my acid is this right here, 0.049 moles, but remember, that's going to be used up. So I subtracted from my weak base, and so when I did that, I got 0.026 moles. Since it's used up, I end up with 0 moles, and then I add that much to my conjugate acid portion. All right, and then, whew, hallelujah, I got some base and some conjugate acid, and so what does that mean? I get a Henderson-Hasselbalch this thing. Thank God we at least get it in with some Henderson-Hasselbalch. I don't want to do another ice chart at this point. All right, but the problem is, of course, is pH equals pKa. They gave me Kb. Actually, they gave me nothing. I had to look up Kb on my own. All right, so I had to look up Kb in the appendix of the book because I'm noticing they didn't give it to us. And it tells me it's 1.8 times 10 to the negative 5, but remember I need Ka. So it's 1 times 10 to the negative 14 divided by the 1.8 times 10 to the negative 5. So Ka is 5.56 times 10 to the negative 10. So then I'm allowed to use my Henderson-Hasselbalch. And again, normally you would change these to molarity, but because we would be dividing both by the same number for the dilution of the two, you don't actually have to do that. All right, so pH equals pKa, so that's negative log of my 5.56 times 10 to the negative 10, plus log of my base, which is my 0.026 moles, over my acid, which is my 0.049 moles. Ooh, sorry, this is running into each other. All right, and then once I solve for that, I got 8.97, which of course makes sense because we did not neutralize all of the base, so we would still have some excess base. All right, so let's keep on going, see what part B is. Hopefully we don't need to use quadratic formula in any of this stuff. All right, and the end. So finally, we are done with equilibrium, or are we? I'm just kidding, we are done. We're done with equilibrium. So y'all, if you made it through chapter 15, 16, and 17, mainly 17.3, you can do this, okay? So we're gonna move away from equilibrium. We're gonna finish out with thermochemistry and thermodynamics and electrochemistry, which are all much easier than doing a titration problem.